So in this video, I'm going to go over the 3-page AP Statistics test reference sheet. Now, remember, on this online version, you will be able to have your own reference sheet and formulas, but this one's included with the exam. I thought I would go over it just to tell you what it has and what's important and what's not important. Because actually, some of these things are obviously things you want to know. There's a bunch on here that either they removed from the exam or your calculator does it for you and you don't really need them. So I often wonder why the reference sheet has a number of useless formulas on it, because even if we did the entire course, there's a bunch of them that are just never used. But I wonder if it's just there maybe to confuse you or see if someone went over it, all right? So this file is uploaded onto Google Classroom, so you can have a copy of this, and like I said, this will be attached to your exam as well. So I'm going to go over the 3 pages, starting with page 1. The top of page 1 will have formulas. It's not formatted all that great. It's just kind of just standard list of formulas here. So the first section of the first page says descriptive statistics. So these are a bunch of basic formulas. Most of them on this page are not necessary or neat or that you won't use them. Basically, I will point out the ones that are important. So starting with this formula, this is X bar, which means how to find the average. It's a fancy way of writing add up all your items and divide by the number of items you have. This is how you find an average, but remember, your calculator, if you put things into a list, it'll find X bar for you. So even though you probably already know how to do this, you don't really need this formula, because like I said, you can always have technology do it for you. This is the formula for the standard deviation of a list of items. It's written in a bit of an odd way, because normally this thing would just be put up top. Like I said, I think they just write it this way to try to be more confusing. This formula you don't need either, because the calculator, if you put items in a list, will get the standard deviation for you. You might want to at least understand the concept of it. So remember, with this, how you find standard deviation is take each one of the members of your list, subtract the mean from it, square those values. That way it gets rid of whether they're negative or not. It'll just make everything positive. It adds them all up, and then once you have that sum, it divides by n minus 1 and square roots. So rarely is it important to know the concept of how the calculation works, but you're never going to need to do this by hand. So understanding how standard deviation has come about, that these are the deviations, and basically they're squared, added, divided, and then square rooted, is mildly important. But overall, this formula, you're never going to need to use this. Like I said, if you want standard deviation, just enter into a list. This next formula, we're not even going to talk about at all. You don't need it. Don't worry about it. It might as well just not even be on here. The next formula, this one is probably maybe the most important one on the page. It's actually something that you do want to be aware of. It's the regression line formula. So remember, a regression line takes an X value and makes a line of best fit and then predicts a Y value called Y hat. So this is the structure of the line of best fit. Basically, it's Y equals MX plus B, but written in statistics language. So B1's the slope of the best fit line. B sub 0 or B naught is the intercept of the best fit line, and Y hat is the prediction that it makes. So the real values are X and Y. Given X, you can make a prediction of Y that's on the best fit line, the line that's as close as it can be to all the data points at once. All right. So sometimes they call it the least squares regression line. Sometimes they just call it regression line. Sometimes they call it line of best fit. There's lots of different names for it, but just realize this is the structure of the best fit line. So this is important. If you need to make a best fit line, you want to make sure you get that structure. This basically finds the slope in terms of the individual points. Once again, this is not something you need to know at all. You're never going to take all the individual points and try to calculate the slope from them. Once again, technology can do that for you. If you put all your data into two lists, the calculator can come up with the slope for you. So this formula is pretty useless. You don't need it. You're never going to need to plug anything into this. So that's another one you don't need. This one is basically a rewrite of this formula. It tells you how to find the intercept. I would use this formula, but remember when we went to find the intercept, once you knew the slope, and the slope formula is to follow, but once you know the slope, to find the intercept, we took the slope, we put in x bar and y bar, because the dots that you get on the scatter plot don't have to be on the line of best fit. If you remember from our notes, the one point that does have to be on the line of best fit is the average of the x's and the average of the y's. So that's x bar, y bar. This formula is basically a rewrite saying if you want to solve for the intercept, you could put in x bar, y bar, and then it just moved this term over. So basically they plugged in x bar, y bar, then solved, so b sub 0 is by itself. It basically says if you want the intercept, do the slope times x bar, do y bar, and then subtract that other term off. So this will give you the intercept. But we never really use this either. If you just know this formula and you just put x bar, y bar into it, it's essentially this part. So this is kind of what we would do with this to find the intercept. It's like that one step. So these are sort of two sides of the same coin. This next formula, another one you never need to use. This would be, if you knew all the points, it would give you the correlation coefficient. Once again, you never need to do that by hand. You can always just put data into the calculator and it'll get the correlation coefficient for you. Just make sure that you have like the diagnostics turned on to the calculator. So this you never need. You don't need to get the correlation coefficient this way. You could just take this formula right off the sheet. It wouldn't matter. This is probably the last formula on the sheet that's actually somewhat useful. So notice the only ones that have any use to them are the regression ones. This one, and then this was how you find the slope. If you remember, the slope of the best fit line is the correlation coefficient times the standard deviation of y over the standard deviation of x. So this we actually used in class if you go back through your notes. So basically these three formulas together get you the line of best fit. This calculates the slope for you. Once you know the slope, you could use x bar, y bar to get the intercept. And once you know the slope and intercept, you can write the best fit line. To start with this, when we did this in class, to make the best fit line, remember we need 5 pieces of information: x bar, y bar, standard deviation of x, standard deviation of y, and the correlation coefficient. So between those 5 pieces of information, you can make the slope and the intercept of the line of best fit, and then make the line of best fit. This last thing has to do with doing inference on the slope. That was taken out of the course, but on the exam. But even if we did do it, we would never do it by this formula. So this formula is another one that you could just cross off. So of all the formulas in this entire sheet of the front, the only 3 that really are going to be potentially useful to you are this one, and this one, and they all have to do with the line of best fit. All right, so that covers the first page. Let's move to page 2. Page 2 has some useful formulas, just have to know how to handle them. Some of them are useless as well, so we'll look at them. Section 2 is probability. This was probability of an OR event. Remember, the probability of A or B was the probability of A plus the probability of B, but if there was overlap, if these weren't disjoint, then you had to subtract what was both. So basically, you take the probability of one, probability of the other, and then subtracting the probability that's both. This is that over count, so you want to remove it. If something's in both groups, you don't want to count twice, so that removes it. All right. This formula can also be somewhat manipulated. You could rewrite it with certain terms moved around, but in general, if you want the OR probability, a lot of times it's just done conceptually, but once in a while this formula comes into play. This is another formula that, once again, we did a lot conceptually, but it's here in symbol form. It's basically the probability of A given B. So if you want the probability of A given B, remember that means you want all the things that are both A and B out of things that are just B, and that's what this means. Basically, you want to find all things B, and then find all things that are A and B, so all things within B that are A, and then divide those, and that gives you the probability of A given B. So it basically limits A to only things that are within B. So once again, we've done this conceptually. It's here in case you need it. So these are 2 probability formulas. They can be useful. So be sure to know that they're there just in case. These 2 were for like expected value and the variance, which if you take the square root of this, you'd get the standard deviation. So when we were doing probability distributions and you wanted to know the expected value of the variance, this formula basically says you would take and whatever the value of one of the events was times its probability, and do that for each category that you'd have and then add them up. So basically, if you had a probability distribution, like maybe it was like rolling a die, your chance of getting 1 was 1/6, 2 is 1/6, 3 is 1/6. If you wanted the expected value, you'd take each value times its probability, and then once you got for the die, it'd be 6 values, you'd add them all up. For the standard deviation, it was once again more complicated. It's like the other formula. You have to take your values, subtract the mean, square it, add them up, and in this case, you had to weigh them by the probabilities. Then, if you want the standard deviation, you have to square root all this. These are normally not necessary because, once again, these can be done in a calculator. If you remember what we did in class, you could put two lists. If you make one list the values and the other list the probability weights, and you run, I believe, one variable stat, it gives you these values. So once again, these you never actually need to know. Though this one, of the two of these, this one's probably the most handy. If you don't have to spend time going to the calculator, if you have a small probability distribution, maybe you have 4 or 5 values, it might be faster just to multiply the values times the probability and add them up for the expected value. But overall, these are also in the calculator, so they're not really necessary. Going forward with some more probability formulas, there's the binomial distribution. The binomial distribution looks a little different than the way we wrote it. This symbol means the combination of n taken k. So we wrote this C, n, k. Then we had the probability of success and the probability of failure. Now, when we wrote it, we wrote P and Q. Instead of writing Q, they just write 1 minus P. And then for this power, I think we had, I'm trying to remember, I think we used C, N, and R or something like that. Basically, it's using these two letters k, so it's a combination of n taken k. N is the total number of trials, and k is the number of successes. All right, so this is combination of these two numbers. And like I said, this is the number of successes, and n minus k is the number of failures, essentially. It's what's left over. So this would be P and Q, and I said this is the combination. So I would, since you have access to the notes, I'd probably just use the formula from your notes as opposed to this, but once again, this is representing the binomial distribution. The binomial distribution has a mean and a standard deviation. The mean is n times P, so if you know the probability of success and the number of trials, this is probably a useful formula because I said there's no real need or reason to go to a calculator for this. It's easy to calculate. The standard deviation of the binomial distribution, so how spread out is a binomial distribution, well, it's n times p times q under the square root. Remember, this is just 1 minus p is q. So I don't know, once again, I think they're just writing it that way to confuse you. So these are all the binomial distribution. The binomial distribution, how it's created, and then its mean and standard deviation. Then it starts getting to inference. When we did inference, we had proportions. So this is if you were taking a sample proportion. The mean of your sample proportions would just be the population proportion. And then the standard deviation of your proportions was square root of p times q over n. Once again, they don't write q, they write 1 minus p. So this is basically like when we were pulling out of that box all those proportions, like the proportion of tags that were under 1960. Remember, it was around 30%. Well, we'd expect our mean of all of our samples wouldn't all be 30%, but they'd hover around that. If we averaged them, they'd come out just about 30%, in theory, perfectly 30%. And then how spread out would they be? Not everyone got 30%. The spread, because remember it started making that normal curve, the spread on that normal curve would be this. It'd be square root of p times q over n. That also happens for distribution of means. So this is like the n stuff we were doing in inference. Basically, if you had a bunch of sample means, the mean of the sample means is the population mean, and then the standard deviation for that was the standard deviation of your list over square root of n. So this is the population's standard deviation, I should say. Basically, these are those same formulas that we used. Normally we had S over square root of n, but this is basically if you have the population information. All right, this also has a normal distribution, but normally what we would have is we wouldn't have this value, so we would end up using a t distribution. These are just for inference. They're repeated on the very last page. So the last page probably has the most useful formulas if you were taking the exam without your own notes. Because the last page is inference. So they call it inferential statistics to sound fancy. They give you what's called the test statistic. This is basically finding a z-score or t-score. So if you want a z-score or t-score, you take your value. Remember, your sample value is the statistic. The parameter is usually the population value or the hypothesized value or whatever you're talking about. So this is usually whatever the population is supposed to be, or the measurement for the population. So you're taking your value minus some set value and then dividing it by the standard deviation or the standard error if you don't have the standard deviation. This is basically how we always did a z-score or t-score. It basically finds how many standard deviations you are away from the mean. So this being the mean, this being your value, and then dividing. Like I said, this would give you a z-score or t-score, which you could then use. They do give you the structure, general structure of a confidence interval. This is important, but it's also on that inference sheet I gave you, which is better than this. But just to go over it, a confidence interval is your measurements or your statistic. The statistic is, your sample value. Do your sample value plus or minus. The critical value is either z star or t star. And then this is usually standard error, but if you happen to know the standard deviation, you could use that too. So this is building confidence interval, your point estimate plus or minus the number of standard deviations you go out times the standard deviation. And then that'll make this, remember this critical value, z star or t star, is based on, I don't remember what I was going to say. It's based on confidence level. So if you're at 90%, 95%, 99%, and if it's a t-score, you have to use the correct degrees of freedom. Then they do give you one sample and two sample formulas. So if you're doing means, now when we learned them in order of proportions than means, but on the sheet they have means then proportions. I don't know why, but once again, that's how they did it. So if you have a single mean, this is the standard deviation of the sampling distribution. Normally we don't have this, so you realize you can put S in there. Normally we use S over square root of n. Sorry, they do have proportion here. So yeah, they go mean first, then proportion. So for sample proportions, it was square root of p times q over n. So this is if you have a one sample or one proportion interval or test. This is how you get the standard error, essentially. These are standard deviations, but normally with this, I said, we put the S in and we get standard error. With this one, we're normally putting in p hat and q hat because we don't know the population values. So normally we're using these as standard errors with the estimates of these S, p hat, q hat. All right, so this is for when you're doing single inference. This helps you with tests and confidence intervals. And then lastly, the two sample cases. So if you're doing two sample intervals or tests, basically for a difference of means, this is the formula if you know the population standard deviations. Once again, normally we don't know these. These are normally the S's, so we get standard error. So we would do S1 squared, S2 squared, N1, N2, add them, square root them. All right. I would ignore this. You don't need to worry about. I mean, this is just saying if these were equal, this is how the formula would work out. If they're equal, just use this formula. I don't even know why they bother with this. So you don't have to worry about this bottom part. If you have difference of proportions, you can use these formulas. Now, once again, this I wouldn't even bother with. But with the difference of proportions, this is P1, Q1 over N1, P2, Q2 over N2. Now, normally you're putting in the P hats for these because you don't know the actual population values. But if you know them, you can, say it's the same formula. But I said if it has the hats in it, then it's called standard error. But this is the general structure of the formula you use. You want to be careful that if you are doing a test with proportions or difference of proportions, that you make sure that you use the pooled values in here. So if this were difference of proportions hypothesis test, instead of using P1 hat, Q1 hat, and N1, you'd use and then using the using P2 hat, Q2 hat, and N2. You would just you'd find the pooled value, use the pool value for everything. So you use P pooled, Q pooled, P pooled, Q pooled with the hat on it. All right. So anyway, these formulas are here for inference. This thing at the very end, we never got to. It was removed from the exam. We'll do it after the exam's over. It's called the chi-square test. So you won't have to, normally this might be important, but since this was removed from your exam, they're not going to ask anything about this, so you can remove that. All right. So those are the 3 pages and what's important out of this reference sheet. If I were you, since you can make your own, I've given you a sheet with all the inference on it. But some of the stuff from here that might be handy is if you made a list of your own probability formulas, if you make sure you know about the binomial distribution, we also did the geometric distribution, and the stuff about making the line of best fit, you could probably do a better job than this sheet does. But if you have the sheet, this is what's available to you, given to the test, besides what you've already gotten. So this is what they're giving you. If you need to reference anything, you can take it off this sheet. And hopefully I've pointed out what's important and what's not important. All right. Once again, make your own. I use this as a model and get rid of the formulas you don't need and add some of the extra formulas that aren't on here. All right. So hopefully this gives you a guide to this, and good luck on the test.